Welcome back. At this point, we are wrapping up our journey through limits, talking about limits at infinity, and in the following video, the intermediate value theorem. I have some text up here, right? We have the limit as x approaches infinity or x approaches negative infinity equals some defined value, ideally, if f of x gets closer and closer to L as x approaches infinity or negative infinity. So, I think I mentioned this earlier in previous videos. The big trick to calculus is simply the young adult version of algebra 2. Okay? Because this idea here is not new whatsoever. In fact, you've come across it quite often. We call this exploration in calculus the long-term behavior of a function, which is nothing more than the horizontal asymptotes. Okay? Because to get a limit or an infinite limit, limits at infinity, for a continuous polynomial function seems silly because it's continuous, so it's going to continue on towards infinity or negative infinity, right? It's going to continue to grow or decline. So more often than not, we'll see these types of, or we'll experience these types of problems with rational functions. Now, limits at infinity do not always exist. And what I mean by do not always exist, because if like the limit is infinite, right, it tends or converges towards positive or negative infinity, yes, it technically does not exist, but like these don't exist whatsoever, right? We can't actually even pinpoint where they are. There are my favorite functions, sine and cosine, because they love to constantly oscillate. Between -1 and 1, so they can't seem to make up their mind, therefore we lose hope in them and move on. Okay, so quick theorem. For all n greater than or equal to 0, that is key. Limit as x approaches infinity of x to the n equals infinity. And this is what I had just talked about with continuous polynomial functions. Now the limit as x approaches infinity of x to the negative n, this now becomes rational, right? Because we have 1 over x divided by the n power. Run out a little bit of space. Okay, so for substituting values in here, regardless of what this value is, right? So we got, let's just assume this is 1. N is 1, right? So 1 over 2 to the first, that's 1/2. 1 over 3, 1 over 4, 1 over 5. So our fractional value is going to continue to get smaller and smaller and smaller. So by the time we get to 1 over 999,999,999,999,999, it's tiny. It's so tiny that we can say it is practically 0. Now, we do have, I guess, a part 2. If n is a whole number, the limit as x approaches negative infinity, right? These were both positive. So the limit as x approaches negative infinity of x to the n, we are going to have two types of behavior. Right, positive infinity, even though we're looking at the behavior as it's going leftwards along the x-axis, because with an even powered function, a negative times a negative will always yield positive. And when the degree or the power of the function is odd, it will tend towards negative infinity because of that additional negative that we must multiply through. Right, so these two correlate. So what's the deal here? If we have the limit as x approaches negative infinity of 1, oops. Well, that's where we would get to, right? So x to the negative n, which is really 1 over x to the n. Well, regardless of whether the degree of the rational function, even though there's not really a degree of rational functions, this power in the denominator is even or odd, it's still going to get infinitely smaller and smaller and smaller and smaller and smaller, to the point where we could say that it's really just 0. But enough of that, let's get into at least an application of this. So let's say that we have a limit as x approaches infinity of this beautiful rational function. And for those of you that have some maybe calculus experience, yes, you're probably jumping out of your chair right now because you already know what the answer is, but baby steps, let's establish a solid foundational understanding. That way we don't have to just rely on these tricks that we've just seemingly acquired over time. So if we substitute this in to the numerator and denominator, we can see that we're going to get some indeterminate form. Okay. Indeterminate form means we need to apply some type of algebraic manipulation. Use blue. So what we want to wind up doing is we want to divide the numerator and denominator by the highest power. The highest power being x to the 5th. Right, so I'm going to multiply x to the 5th, sorry, x to the negative 5th, because we're dividing, to both the numerator and the denominator. Okay. So here, if you remember your exponent laws, this will yield the 20x to the 3rd minus 3x to the negative 4th. Here, this will simplify all together. Be left with 3 minus 4x to the negative 3rd plus 5x to the negative 5th. Now you might be sitting there wondering, well, what does that do? Why does that really help us? Well, remember, this, even though it looks dramatically different from our visual function, is still behaving the same way as this because we've modified it by a factor of 1, since we've done the same process to the numerator and denominator. So we can now reevaluate our limit. Since all of these exponents here are negative, these are really fractions, right? This is really 20 divided by x to the 3rd. This is really 3 divided by x to the 4th. So on and so forth with these two terms. Therefore, if we substitute infinity, this is now going to become a 0, become a 0, become a 0, become a 0. We're not direct substituting here because this is a constant value. We're left with 0 divided by 3, which is 0. So we know that for this rational function, as x is approaching infinity along the right axis, or along the x-axis, the behavior of the function is just going to come and coast and kind of sit along that axis. And what's, I guess, the takeaway point here? You're either a student in calculus in high school, or you're a college calculus 1 or 2 student. You've been doing this for years. It all started in Algebra 2 when you started sketching your first iteration of polynomials, and then you built upon that in pre-calculus with maximum minimums, and now we're starting to introduce more specificity here with limits in calculus. So I kind of consider calculus like Algebra 4. So nice job. Now this, though, can start to get extremely time consuming, and the more we rely on algebra, the more we open up the possibility to making some careless arithmetical mistakes. So we have a second theorem for this lesson, which says the asymptotic behavior of a rational function depends only on the leading terms of its numerator and denominator. If the first term of both the numerator and denominator do not equal 0, then the limit as x approaches positive or negative infinity of first term, first variable, second term, second variable, so on and so forth, right? Because this is a leading term, that would have to be 1 power less, or 2 powers less, or some power less constant term, and vice versa, and the denominator But wait, how come we're just focusing on the coefficients? We can't forget these, right? They're variables that are attached. So we really have the ratio of the leading terms times the limit as x approaches positive or negative infinity of, or quotient rule for exponents, okay? And this is critical because we're going to have, if you remember back to Algebra 2, 3 different scenarios, right? We're going to have one where the degree in the numerator is larger than the degree in the denominator. Scenario 2 is going to be where we have equivalent degrees, and scenario 3 is where the degree of the numerator is less than the degree of the denominator. So I'm going to try and get that all in this space. Probably going to fail miserably, but yeah, you do what you can encoded. Right, so let's say we have the degree of the num is equal to the degree of the denom. 3x cubed plus 5x minus 2 over 4x cubed minus 2x squared plus 6. Okay? So we're really just focused on what is happening with the leading terms, right? Because if we applied, not here no more, but that division by the highest degree, if we divide out everything by x to the third, these terms here would reduce to zeros, and then we'd have just the coefficients here. So let me erase this piece, since you should have jotted that in your notes by now. But using this theorem above, right, we have the ratio of leading terms times the limit as x approaches infinity of x cubed over x cubed, which is really just 1, and 3/4 times 1 is 3/4. Voila. Scenario 1. Scenario 2. Degree of the numerator is greater than degree of the denominator. So let's assume that this equation stays exactly the same, except I'm going to make the degree now 5 in the numerator and leave everything else the same. We once again have the ratio of coefficients for the leading terms, and we have x to the 5th over x cubed, which will yield x squared. But when we go to substitute that infinity, this becomes infinity squared, which is infinity. 3/4 times infinity yields an infinity. And similar to the rule that we were applying in our initial example, we have the degree of the numerator is less than the degree of the denominator. So I'm going to use the same equation again, except here I'm changing that first term to, in the denominator, to 4x to the 5th. So yet again, 3/4 times the limit as x approaches infinity of x cubed over x to the 5th, which is really 1 over x squared. And we know that that will become a 0, and 3/4 times 0 is 0. So there are your 3 scenarios, right? One where they're equivalent and the long-term behavior is simply the ratio of coefficients of the leading terms. One where the degree of the numerator is larger, so the long-term behavior is that it tends upwards. And this you have to be careful, because if this was x to the 6th and we have x cubed and this was negative infinity, then we're going downwards, so just be mindful of your signs. Right, and then last but not least, the degree of the numerator is less than the degree of the denominator, so we're going to have this 1 over infinity situation, which will act like a 0 and ultimately force our end behavior to coast along the x-axis. Before we conclude this video, I know it's been a long one, just want to do 2 more examples, because this can get a little confusing. So we have a limit as x approaches infinity of 3x to the 7/2 plus 7x to the -1/2 x squared minus x to the 1/2. Okay, rational function, limit at infinity, therefore we can just kick in that theorem. Boom, remember there's an imaginary 1 here. This is nothing but, this is a 3.5, that's a 2. So we have 3 divided by 1 times the limit as x approaches infinity of x to the 7/2 over x that, which is going to be really x to the 3/2